Sapien is a simulation platform for vision, learning, and robotics research. In its first version, Sapien supports physics and robotics simulation, rendering, and provides a large set of assets of articulated objects. The physical simulation in Sapien is designed to closely resemble the real world. As shown in this video, the robot in Sapien Simulator on the left is executing the same trajectory as in the real world shown on the right side. The simulated objects are manipulated through contact and friction forces, and the robot uses a PD controller to follow the trajectory just like in the real world. On the other hand, the large-scale simulation assets allow Sapien users to design many manipulation tasks. For example, in this video, Sapien assets are used to construct a large-scale manipulation scale benchmark for household tasks. Now, we introduce the next version of Sapien, Sapien 2.0. In this version, we further extend Sapien to include motion planning, improved rendering, accurate depth sensor simulation, and an extensive UI system. Let's start from the renderer. On top of this real-time renderer provided in Sapien 1, Sapien 2 has allowed unlimited number of shadow casting lights and ambient lighting from environmental maps. The renderer is now implemented in Vulkan with customizable shader pipelines and render targets, such as albedo, normal, and depth. If you want to render photorealistic images, Sapien also comes with a ray tracer, with an optional denoiser when using an NVIDIA GPU. The ray tracer also enables realistic depth sensor simulation through active light. To look at this simulation, let's first zoom into the robot camera. Similar to a real sensor, we project light pattern onto the scene and use stereo vision to compute the depths. With ray tracing, our renderer produces realistic artifacts caused by occlusion, translucency, and specular materials, resulting in a realistic depth. Let's move on to our motion planning library, MPlib. Here, we first instruct the robot to move its face to the designated position. Next, we instruct the robot arm to move to its grasping position. We show the trajectory planned by MPlib with collision avoidance on the left and no planning on the right. And finally, we instruct the robot to place a plate onto the table. MPlib takes the robot model and scene point cloud to avoid collisions and plan the trajectories. It is a simple and powerful tool that can be integrated into many manipulation tasks. Next, let's move right on to a showcase of the convenient Sapien viewer. Here, we can easily navigate around the scene with a mouse and keyboard, or focus on objects. It also provides annotations for object pose, joint axis, and camera placement. We can select here to view rendering modalities like normal and segmentation. When we select an object, we can find its physical and visual properties right here and easily see its collision shape. When working with the robot, the viewer allows viewing and editing joint angles and joint controllers. It also contains a built-in inverse kinematics solver, so we can easily change the pose of the robot. We can also easily edit the scene, such as moving objects around and moving the lights. The best part of this viewer is that all its functionalities are coded in Python, so it allows endless possibilities in customizations. Now, let me introduce some concrete use cases of Sapien. Sapien has been applied to design human teleoperation systems, manipulation benchmarks, transferable vision models, and robotics education packages. In the first example, the users have customized the Sapien viewer to allow using human hands to control the simulated robot. This allows them to conveniently collect data for imitation learning. Next, Sapien assets have been used to construct the Sapien Manipulation Skill Challenge, or ManiSkill, to test the generalizable manipulation across objects. It features visual point cloud inputs and physical interactions. ManiSkill Challenge also includes large-scale demonstration trajectories collected through reinforcement learning environments built with Sapien. Next, Sapien has enabled 3D vision models trained on simulated data to transfer to the real world, thanks to the realistic depth sensor simulation. Here, by generating training data in Sapien, the post-estimation model directly transfers to the real world without any fine-tuning. Finally, the rich robotics support and simple API make Sapien suitable as an educational platform that's been used in multiple courses to let students gain hands-on experience with robotics control and planning algorithms. To summarize, Sapien supports realistic physics and sensor simulation, provides rich assets and convenient interfaces. It enables many downstream applications. You can try out Sapien with pip install Sapien on any Linux system